So our first speaker, that's Andrzej Krzemieński. He has over 10 years of professional C++ experience. He has taken part in forming the standard of C++ and also is an active maintainer of one of the Boost libraries. You might know Andrzej from his C++ blog, which is called inconspicuously Andrzej's C++ blog. And today he's going to talk about, I guess, a very important factor in software development, which is something that we can always find in any program. That's probably the only thing that we can find in actually every computer program, which is bugs. And we don't really want them there, but there usually are. And we want to get rid of them as soon and as early and as possible. And that's what the talk is going to be about. So let's welcome Andrzej Krzemieński with his talk, Fewer Bugs.
Thank you. Thank you. I've been coding for about 12 years, and I cannot accept the fact that still I'm planting bugs in my code. And so do my colleagues, which are even more experienced than me. So a lot of my time is devoted into trying to figure out what's the reason for it and what techniques I can apply to avoid them in the first place. And this is what this talk is going to be about. So you detect and fix bugs at different stages of development, but it's quite obvious that the later you find them in the game, the more expensive it is to fix them. And the expense is not only measured in time and money, but also in damage done to hardware, human life, or the environment. So our goal in general is to move the the bug detection to the earlier stages of development, where we code, where we're still at the desk and can react before anyone can see it. Only then this is a good approach to dealing with bugs. There is a lot of ways to do it, like unit tests, thorough code reviews, or using all sorts of static analysis tools. You should, of course, employ all of them, but our talk today will only focus on using the compiler and taking its type system to the extreme. Okay, so this is going to be 5 topics, quite independent, but they all boil down to the same advice, that you can think of code as not only something that's used for generating binaries, but also something that communicates your ideas to fellow developers and to tools, like analyzers or the compiler. And the first one, okay, it's about writing interfaces that are not ambiguous. And what do I mean by that? This is an example of a code. I'm checking if I'm done with some job, and I'm calling vec_empty. And it's obviously a bug. I probably meant to call vec_clear. Well, I called vec_empty. Well, if I'm experienced after a couple of years of working, if I got hit by this bug already, I know which method I should call. But if I'm new to the STL, and if I worked in another library that chooses a different naming, the problem is that word empty in English can mean 2 things. It can either be an adjective and say, tell me if this container has no elements, or it can be a verb to say, just wipe out all the elements. Of course, if I read the documentation, I would be done with it. But if I'm used to using function empty, and before we had STL, there were other attempts to do a similar library. One of them was Ragwave library, that they use exactly this name empty to mean wipe out the elements. So if somebody with this background comes here, for sure the first program he makes, he will get this bug. And to fix it, if we were able to move back in time, it's quite simple. It's just to use a bit longer name, which has only one meaning, doesn't have this second possible interpretation, and only this, the change in name, would have avoided a number of bugs in the past. It's not the case today, because today compilers are able to detect something like this. You are calling a function that doesn't alter anything, returns a value, you ignore it, they will warn you. But if you are not lucky with a newer compiler, or if you were writing in the past, this used to happen from time to time. Another example from the standard library. We all know this RAII idiom, which boils down to saying you acquire the resource in the constructor, and you release the resource in the destructor. And the unique pointer is a natural example of this code. So in the constructor, you acquire some memory, it will release it in a destructor. If you need to release the memory before the destructor is called, you can call function release, but does function release really release anything? If you worked for a while, you know it doesn't. But the first time you are using it, it is likely that you will get it wrong. And again, it would have been better if this function, this is not a C++ now, but if this function was renamed to something that doesn't have the potential to confuse you. I'm using a third-party library which deals with threads. I need to put my thread to sleep for a while. I call this, it has this obvious function sleep, and I sleep for 10. And this is 10 what? 10 seconds, milliseconds, something else. If you are confused, if you find this suspicious, you win, because you will look it up in the documentation, in the implementation. You will get it right. The worst what can happen, if you don't have to look it up, because you already know what it means. Like if you come from a Unix environment, in POSIX, threads sleep in seconds, so it's obvious to you, it may be obvious to you that this is seconds. You don't have to even check it. If you come from Java, in Java, threads sleep in milliseconds, so it may be obvious to you that this is milliseconds. Now, if you get two people like this in the team, the bug is imminent. And a similar situation, if I want to call some function, some callback, not now, but at some future, I have this timer, I give a callback and some integer. And now this is what? This integer. This is supposed to be milliseconds since now, or is it supposed to be a date encoded in some format? You don't know. And you will surely be confused and perhaps will get it wrong. And this problem is nicely solved in a C++ standard library. And the choice they did is to not even give you function sleep. Instead, you get two functions, like sleep until, and now it's clear that the argument that follows represents a time point rather than duration. And conversely, you get sleep for, and only from the name of this function is it obvious that the argument that follows is the duration and not the time point. And you cannot pass me 10. If you just try to pass me 10, you will get a type system error, because the interface requires of you to be specific about the unit. So you either have to say that it's seconds or that it's milliseconds. In this example, I chose to use this new feature of user literals. There are other ways, but all these ways force you to tie the unit to the numeric value. So the numeric value is never alone and does not confuse anyone. Next example. It's boolean arguments in function calls. I give this run, true, false, and what's true and what's false? You don't know. This problem is not seen by whoever writes this function, because from his point of view, he sees the name, so he knows it's obvious to him. The first bool says whether we want to use some computing engine, the other says that we want to skip something. It's obvious, so he doesn't have any problem with it. But we do, and you probably didn't notice it, but I wanted to pass the arguments the other way around, but I confused them, and I didn't notice it, the compiler didn't notice it, nobody notices it. And if you have more of this in the code, you're just tired of looking at it, you will just, even in the code review, you will probably skip it. So once the bug is found and reported to me, and I fix it, I will probably put the comments inside function call to indicate what my intention is here. But even now, I could get the comments the other way around. It almost looks as if I'm asking for a language feature, which is called named arguments. This is not in C++ for now, but they're actively working in the committee to add it. We will not get it in C++ 17, but at some later stage, it will make it into the language, because it helps to solve some problems, but not all. For now, we have to deal with it by means of library or our own types. There is more problems than only the function calls. Even for those who write those functions, if we imagine that this is a virtual function and we try to override it, even when overriding it, we can get the arguments the other way around. So we also would like to avoid this problem. And what you can do to avoid this problem is to write your own bool class that doesn't have this problem, or use a template for the explicit library. This is a small library that allows you to write more explicit interfaces. It has a number of tools like that. And it has one solution for bools. It is a template for generating unique bool types that are not interconvertible to one another. So you pass me, you invent some type. It doesn't matter what it is. I just need it to be unique. Like here, I'm just forward declaring a class. I will not even use it. And in exchange, this template generates a unique Boolean type. It has all the Boolean interface, except that you cannot pass me just bool. It will not work. I declare an interface. Now I have two distinct types. One is called skip unused. The other is called use engine. So even the type alone conveys the information as to my intentions. If I just call it with false and true, I will get a type system error, because this is not convertible. This strange use engine and skip unuse types are not convertible from just true or false. You have to perform an explicit cast, and when you do it, you are in a way forced to type by using a type name what your intentions are, what this particular bool is supposed to represent. And now the compiler can verify it. If you did them in the correct order, the compiler accepts it and the program works. If you pass the arguments the other way around, you get a type system error. So a number of bugs is wiped out only because you chose a different type of bool in your interface. And it also works nicely with function call forwarders. If I have this std function, it works nice with them. Also, this safety feature is preserved because this use engine is a regular type, which can be perfect forwarded. And therefore, it works well with all kinds of type erasure, with virtual functions, and other things like stud function. For the last example, I will need to do a 2-minute introduction to Unicode. Unicode is able to encode any practical symbol you use in writing in probably any language. So if I want a letter U, there is a code for this. If I need a less common letter U with a macron, which says that I should pronounce U for a bit longer, there is a Unicode code for that. A V with a macron doesn't make sense because you cannot prolong the consonant. But if you insist on having it, the Unicode will not waste its space, but it allows you to build it with 2 Unicode code points. First, you just type normal V, and then you type a combining character, which doesn't has a meaning on its own, but it says how the preceding symbol needs to be modified. So by using 2 Unicode code points, you can encode a strange letter. And now, when it comes to really storing them in memory, like in UTF-8 encoding, if the letter fits into this 7-bit ASCII scheme, it will consume only 1 byte in memory. If it's less popular, like U with a macron, it will consume 2 or 3 or 4 even bytes. What is of interest to us here is that you may have, if we consider this V with a macron, you may have 1 graphical symbol, or graphem, as they call it, but 2 Unicode code points, but 3 UTF-8 bytes. And now the question. We'll be writing a UTF-8 string, because we are missing it from the standard. And as with any other string in the world, we will provide function length. And what should this function length return? Number of bytes, or the number of Unicode code points, or the number of symbols, or these graphemes. And now, anyone dares to answer? What's the best choice here? Symbols. An error. Okay, I suppose it depends on where you come from or how you see this being used. If you think about user password and saying that type no less than 6 letters. So okay, you will think in terms of symbols, and this may be a natural choice for you. If you are concerned with memory usage, you will probably think that the bytes is the natural choice, because this is the size. If the string is a container, the container contains those bytes, or perhaps code points, if you think in abstract terms of a Unicode. Whatever particular answer you give, you will confuse someone in the future. So I would agree with you that the right answer to this question is not to provide function length at all, because it will confuse out people. Instead, provide 3 functions that in their names clearly reflect what you are doing inside. It may be a difficult decision, because every other string in the world does have this length function. But so what? Our goal is not to mimic anything else they have. For other strings, this might be a good choice, or not. Who cares? For our particular task, for sure this would be a bad choice. So then choose it. The second topic deals with what I call unwelcome values. We'll start with a short code. You probably have seen a condition like this quite often. If a pointer is not null and something, do something. And it's immediately visible that the 2 terms in this condition serve completely different purposes. This contains limits, whatever this is tied to business logic. Apparently, this config may or may not contain limits, whatever they are, and depending on this, we may want to do different things. If we chose another language or another set of types, we would preserve this condition. The other one, we never expect this config to be null. If we used another language or another type, we would never care for this. But because we know the pointer passed can be null, and this can cause a undefined behavior, perhaps a crash, we want to avoid it. We would be fired if we were planting undefined behaviors, so we just put an if. But the meaning they have is at very different levels. We need to use a unique pointer because we are taking responsibility for releasing this memory. But if at some later point, we would refactor it to a reference, which is usually a good advice. Use a reference rather than pointer, only because you don't have to deal with this null case. If we were able to rewrite it, we would for sure remove the first condition because it's just gone only because we choose to use a different type. And the other would for sure be preserved because this reflects what we are doing in this program. But for some reason, we cannot do it because we will be releasing the memory. We will have to use a smart pointer. We have to do something else. One option is to use an assertion, which at least sends a clear message that we are not interested in really checking it. It's supposed never to be null. But I'm not really comfortable recommending it because it's embedded in the function body. So for sure, it's better to have it like this than not to have it at all. But apart from you, whoever uses this function may not be able to see your implementation and what you are typing here. So this information that you don't want a null pointer may be just gone. And this would be a shame. So you may need to stick to a runtime if check, but the minimum what you can do is to separate it into another statement. If you think in terms of what code gets generated, it's the same as the initial example. But if you look at the code layout, it sends a clear message to anyone who gets to read this code that the meaning of those two is quite different. If somebody at some later stage needs to refactor this code, he has a hint that he can get rid of this condition, this has to be preserved. It's simpler to anyone to later work with the code. What you can do is just to use another macro so that when somebody sees a macro like this, he's immediately alerted that there is something strange going with this condition. So it may be additional message you send that whoever looks at this code should treat this condition as something else, as only a defensive check, which will probably never trigger the code below. Other people will just wrap it all, both the check and the action that follows into one macro. So it even more separates this defensive code from the program logic and makes it easier, the job easier for whoever reads or refactors the code. What can get out? But there are still suboptimal solutions because the information is only visible inside the function if you have access to the function implementation. Whoever uses this function doesn't see what your assumptions are. Now I'm showing you some fantasy because it's not in C++ yet, but the language feature like this is being developed in the standards committee, and sooner or later it will make it into the language. This is called a precondition, and it's quite similar to the assertion in some aspects, but it has one significant difference, that it is put in a function declaration rather than inside the body. So anyone who has access to the declaration immediately sees what you expect of the callers. And this precondition doesn't check for anything at runtime. It doesn't add any overhead. Its only purpose is to communicate your assumptions to the outside world, to the other programmers, but also to the tools like static analyzer, which can match those preconditions against the code paths they are seeing and warn you if you get them wrong. But this is future, and for now, we have to deal with other tools. And the only thing I can offer here is for you to use a different type. Like here, I have a template that wraps a pointer, even a smart pointer. And it doesn't do anything at runtime, actually, because inside it only will store this unique pointer. But it is additional type that messes with the type system. And this is what I want. I will alter the type system so that you will have to explicitly convert the unique pointer you have to this smart type. You can think of it as a contract. Not a new one, because a unique pointer, the type unique pointer, is already a contract, which says, you allocate this memory, I take responsibility for deleting it. And not null is another kind of contract, which says, you are making sure this way or the other that this pointer is not null, and I'm working on that assumption. I don't have to do it myself. If the user, whoever calls this function, is not aware of the contract, he will try to pass a regular unique pointer to our function, and he gets a type system error, because types mismatch. There is no conversion between unique pointer and this not null. What he has to do is to call this converting function. And this is also a part of this interface, not the type, and a function like makePair that creates this type. And this is like signing a contract. Yes, I accept the fact that I am responsible for guaranteeing that this pointer is not null. He can, of course, dodge the system and still pass us the null pointer, but now he cannot do it by accident. It will be his deliberate choice, and even if this bug occurs, it's clear on which side of the interface this should be fixed. So this basically summarizes what I've just said, that there is no runtime checking or whatever involved. The only purpose of this tool is to be a distinct type visible to everyone around and sending a message in the type name. If you are uncomfortable with not having any runtime checks, you can provide an alternative version of this not null that checks in the constructor when you try to construct this type whether the pointer is not null. You still get a benefit from it, because if you don't do it, if you do it the old way and you get just a raw pointer, anytime you have to use it, you have to perform this defensive check. But if you change your function to use this non-null pointer, the runtime check is only performed in the constructor, and then this type is safe to be used, and those functions that use it can rely on the check performed earlier in the constructor. So instead of n checks, you get one check. And the real benefit can be seen where you don't create this type only before the usage, but you are able to use it across all layers of your program. Then there is no conversions, because a copy constructing from one non-null pointer to another is safe, because you checked it in the previous one. So there is no runtime checks, or there's even less runtime checks, and everything is as short as it was before. Now the third topic, this is something that I call checkpoints. And an assertion is one example of such. We have seen perhaps a suspicious use of an assert before. Now this is what I call the proper usage of an assert. I have some algorithm that copies one array onto another, but backwards. I will iterate one from 0 to 10 exclusive. I will have another index that will go from 9 to -1. One is incremented, the other is decremented. I check only for the end condition on one index, but it's obvious that when I'm done, the other index should be at -1. It is obvious, so my assertion is completely useless, redundant, because I'm stating the obvious. So you might be asking why I'm doing this at all. But this is not for the compiler. This is for whoever reads this code later to see what I was thinking. He can figure out this himself, but after 2 minutes of analyzing my algorithm. I'm giving you this visible immediately. So if you get to fix my code, you will know what you have to watch out for and what I was trying to do. It's the information to other people that need to deal with this code or fix it. It makes sense to assert, and assert doesn't really check anything. It just asserts, declares what's obvious already, but perhaps not immediately. Here we have an example where we can use assertion to say about function inputs, and we can assert that provided that we are in control of all the places where this function is called. This happens when a function is private. Only I can call it, so I can guarantee that I will be calling it only with a subset of allowed values, and only then I can safely assert that this is true inside the function. And this also illustrates that making sure that the precondition is met, like here, doesn't mean that I have to check anything. It's only sufficient that I know the flow of the values. I know that if I multiply one real number by itself, it can never be negative. If I add two like this, they are still not negative. So I know I will be passing a non-negative number, even though I didn't check it. It's not about checking. It's about you being aware of what you are doing. Another example of this checkpoint. You will hear the advice by many people which say that rather than using row loops, you are better off using a dedicated algorithm. And this is true. I wholeheartedly agree with that. But a number of these people, in the same sentence, will inject a big fat lambda like this in the code. And this is exactly counter to the advice they are giving, because this lambda is just a chunk of expressions with no meaning assigned to it. If you look at this OR here, there must be something wrong with it, because assuming that the max is greater than 0, it means I want either the number greater than 0 or less than max, which means any number at all, which is probably nonsense because there are a simpler way to say I'm interested in any number. So I either wanted to type an AND rather than or I wanted, and this would mean just numbers from the range, or I wanted the inequalities the other way, and it would mean anything but the range. But you will never know which one it was because I left you no hint as to what my intentions are. So a solution to this problem would be to go out for a while from the logic flow and create a small dedicated functor which has a name, and this name clearly reflects what you want. This way, this is immediately clear what this function is doing. And also you have a separate unit of work, which you can separately unit test and get additional confidence that you are doing the right thing. And even if I plant the same bug with an OR inside this range, you can immediately evaluate the implementation against the functor name. And only from this you know how to fix it, without thinking what it was supposed to do. If you insist, if you don't like it, and the idea that you will be exposing another type in your interface and you want to keep it private, the minimum what you can do is just to give a name to your lambda. Lambdas are supposed to be unnamed, but you can just give it a name by creating a variable. And this way you have a room, you get this, by this additional place where you can type your intention. And this way your implementation can be evaluated against, you get this checkpoint. Somebody doesn't have to think about it all. He has this stop here. First, okay, I know what this is doing, even if the implementation is wrong again, but at least you know what my intention are, and you can go from this and evaluate the other part, what it means. So if not anything else, you narrow down the scope of the bug, so it's clear where to fix it, and it's easier to spot, because whoever reviews the code has those two steps which he can evaluate separately. Another example of a checkpoint, or rather the lack thereof, is the advice that I often hear, which is called almost always auto. Some people insist that wherever you used to write down the type of the variables you used, you should, for some reason, use just those autos. And the rationale being that since the compiler knows the type already and can figure it out, why force you to type it? Sounds plausible at first, but the problem is that the compiler may know something else than you do and deduce a different time than what you expected. So here, I will be logging some D, which I have made some assumptions on, that it may be something called distributions, but I don't know, it may be something else. It is likely that I will be logging something else that I think I'm logging. I may have picked up what this function is returned, the type of this function, and I can be confident that this is the type I want. But the code tends to change over time, and someone could refactor this distrib to return something else. Like he thinks, well, it returns a distribution. There is a good reason that I will be returning a proxy to a distribution. It converts, it has a conversion to distribution, so it's fine. Whoever needed the distribution gets the distribution again. But I have this proxy which can do something else. But those autos are not immune to proxies. If you get it a proxy, it will work on a proxy and will log something else than you wanted. So the solution to this problem is quite simple. Just write down the type you want to use. It's an information. You can treat it as a check. You check whether the compiler thinks the same thing as you are thinking, because it may not be the case. There may be overloads and you missed it and it's selecting something else. You would rather get a compile time error and fix the problem than live with defaults which are likely wrong. If this is a proxy, you resolve the proxy problem because you trigger the conversion. If this is a different type than you wanted, yeah, you get a compile time error and an opportunity to fix it before the program is shipped. So my advice here would be called almost never auto. Don't use autos unless there is a really compelling reason to do so. There are cases where it's useful, but it doesn't mean that everywhere where you have a type, you can just wipe it out and use auto. And another illustration of the problem where typing the types can save your day is this story. Imagine that I am doing some benchmarking and I'm doing them in milliseconds. This one returns like 2000 milliseconds. I don't care about the type because I'm using this almost always happy auto philosophy. So I don't care about the type, or I care, but I've seen that that measure was returning milliseconds, so I was good with that. And I just take the numeric value and print it out. I get this 20,000. Now, at some later point in time, we observe that it doesn't make sense to return in milliseconds with such huge numbers, so we change it to seconds. And we return 20 seconds. Physically, it's the same, because I also changed the units. But now, because I don't care about the type, I still think it's milliseconds. I get the numeric value, and now I am lying in the result. Contrast this with the situation when I explicitly declare what type I want to work with. If, again, this measure is changed to return the seconds, depending on the library, some other type might have reported a compile time error, and because it would see a type mismatch, but the chrono library from the standard library is quite smart. It observes the type mismatch and applies the implicit conversion. It changes not only the unit, but also adjusts the numeric value. So again, the numeric value is 2000, and you get the same results, even though the type of this function changed silently. That's about checkpoints. Now, some interesting topic about bonus interfaces. We'll be writing a type representing rational numbers. So I want to be able to construct a rational with two integers. First is the numerator, the other is denominator. I give you a constructor which takes the two. Since C++11 we have this nice brace syntax, so I don't even have to repeat the type. I just passing you. It's like I'm converting from more than one argument. And the meaning is obvious. It's 5/2, it's clear. But also, to make it easier for everyone, I give you a way to initialize it with only 2. And the meaning, it's obvious, it means 2/1. So I put a default value of 1. And it all looks nice. But unfortunately, it also allows you to initialize it with 0.5. This is obvious that it is half, but when you really trigger it, there is no conversion from double. But there is conversion from int now. So it converts a double to int, and I get 0, and then 0 we know how to assign to rational. And the bug is imminent. And the worst problem with this is that when you look at the function declarations, you cannot see it. You cannot see that you can initialize the rational from double. You get it. It's part. If we thought of an interface as a set of operations you can do on a type, it is part of an interface. But if you think of an interface as a member functions declared on your type, it's not there. So this is easily overlooked. To illustrate it graphically, this would look like this. We think we are declaring this interface, but owing to the graciousness of the compiler, we get even more functions. Some of them are really useful, because I wouldn't like to type all those copy constructors myself. I'm glad that I have them, but some of them can really hit you. So our task here would be to explicitly declare what we don't want of the compiler to be given. One easy thing would be, if you are lucky and work on Clang or GCC, it has this float conversion warning. If you enable it, it will immediately show you all the places where you perhaps have this problem. And especially if you turn warnings into errors, you sort of have a different language which is safer, and your problem is solved. But you may not want to prevent all those conversions, because sometimes they make sense and are safe. It's only around this rational that we have a problem with it, because there is natural semantics to assigning 0.5 to a rational number. So you may only need to fix it locally around rational, and it may be the case that you are not working on Clang and GCC and you don't have this warning that would help you. Luckily, since C++11, we have these deleted functions, which are the tool exactly for this purpose. Now I explicitly declare that I don't want the other constructor. It's not the same as not having it at all. Deleted function is not a function that's not there. It is there. It participates in overload resolution. But if it gets selected, you get a compile time error, exactly what you want. This is how it works. If I initialize rational with 1, I have 2 constructors. They compete. The first one wins because it's a better match. The program is compiled fine and works as expected. I initialize it with 1.0. The two constructors compete. The second constructor wins. And I get, and now, and only now, because it won, I get a compile time error, which gives me an opportunity to fix the bug I have. And also when you use those type traits or concepts in the future, and you have this deleted function, they are able to observe it and say that rational is convertible from int, but not from double. But rational may have more of those functions that take int and dangerously may also take doubles. And if you try to apply it in all places, it gets tedious, repetitive. It clutters the interface and makes it difficult for somebody to understand the intention. So what you might do to get the solution more compact is to provide your own type, or take one from the explicit library, which implements the same trick but internally. You can use it with ints, but you cannot use it with doubles. The implementation is quite easy. You provide two converting constructors, one taking int, which does the obvious, the other taking double, which is deleted. And it's the same, but it's packed into another tool. So in your interface, you don't have to mess in all the places. Our example with two bools also falls into this category, because I can use it with two bools, but I can also use it with all the various kinds of stuff, and it still works. Okay, I admit that this is a nasty example. No one would type it when they see it's two bools. But suppose run used to have two overloads, one taking bools, the other taking pointer and the size. And I decided to remove the other one. And I hope that the compiler would warn me about all the places that I use it. But it will not, because it doesn't see the previous one, but the one taking two bools is good enough. So it will use it silently. So the solution with this tagged bool also solves the other problem. Not only is it clear which bool represents what, but also you cannot just pass me some numbers, pointers, doubles, integers. All those conversions are wiped out. And the compiler warns you when you accidentally try to use them. Another example of this sort, this is common in job interviews. We have something that represents an array in memory, so we'll be allocating memory in constructor, deleting it in destructor. It all appears fine when you look at the interface, but unfortunately, the compiler will, if you fail to notice it, will generate a copy constructor, which is shallow, and does a real mess. If you try to copy it, you get two handles to the same chunk of memory. Each thinks it will delete it. When the second one tries to delete it, the bug is imminent. Ideally, we would go back in time and just remove this rule that tells the compiler to auto-generate the copy constructor. Since C++11, this feature is deprecated. So if you try to use this shallow copy constructor, it must work because of backwards compatibility, but it's a deprecated feature. And if you are lucky, if you work on Clang, it has this deprecated warning. It will warn you about all these places. But if you don't have Clang, sorry, there is nothing to help you there. The only advice I can give you then is that when you start working with a class that will be managing a resource, the first thing you do, just after you close the brace, is to delete all the special member functions. Only then can you say that you are starting with an empty class. And if you know the rules, that which generation of which special member function triggers or prohibits each other, you will know that if I only declare the first one, I would get exactly the same effect. But if you don't remember the rules, or you think you will forget them, or you're working with other people and not everyone knows these complicated rules, the safest thing to do is just to delete them all so it's clear to everyone around that this is what you are doing. Another example of the same thing. I have something I call processor, which will be working on a big amount of data. Because I don't want to copy it, I will hold it by reference. Because I don't want to modify it, I will hold it by L-value reference to const. So I have a member, you have to pass it to me in the constructor, and this is how it works. This big data is supposed to be created before that. You create a process, you give me a reference to it, and then I can work with it. And it works as expected, but it also works as not expected, because if for some reason a temporary is created, L-value reference to const binds to a temporary, I get a temporary. Next time I try to use it, I have a UB. If I'm lucky, it crashes and doesn't do any damage. Well, it may get even worse. But we don't even want to do that. You may have heard that binding a temporary to a reference extends the lifetime of a temporary. This is so for automatic references and global references, but not for member references. None such case here. This will be a dangling reference. And a fix to this is similar to the fix of the previous one. Just don't catch whatever this is by reference, but provide your own dedicated type that binds only to L-value references, but has a deleted conversion from R-value references. Well, this might sound strange because you have R-value reference to const object, but it still works the way we think. R-value reference to const is a better match than L-value reference to const when you bind to a temporary. So we prohibit all the temporaries. We only bind what we want. Only now do we say what we really want. Only L-value references, no R-value reference. And as was observed by Vicente, those solutions to the rational and to this L-value can be generalized into one wrapper where you give me the type you want to work with and a criterion that tells the good types from the bad types. And in fact, it's implemented in this explicit library. And the last example of this sort, I got an XML file, and I want to parse it into the document object model. The program compiles, but at runtime, it does something else than expected. Because you didn't see it from this call. But function parse XML doesn't really take a string, but a handle to a file in the file system. But the way I define this handle, it takes a string and some other things. But I forgot to make this constructor explicit. And now, even though it has more than one argument, it is a valid conversion. So what the users get, and you cannot see it immediately, is sort of another overload, which just takes a string, but does something else than you might have expected. And you will sooner or later have a bug. And there is no magical tool that will help you. That only the advice we have known for years, that you should make every constructor explicit. I would only add to that not only a single argument constructor, because 2-argument or 3-argument constructors also can be used for conversions, as we have seen just before. But also, since C++11, we have this brace initialization syntax which can deduce the type. And this is almost like a conversion which can take more than one argument. Like here, I have a tool, whatever this is. I have a predicate, and I can return it like this. And you probably didn't notice that I am returning a shared pointer. Because in the standard library, the one-argument constructors are explicit, but the 2 and more argument constructors are not explicit. So you can perform a sort of implicit conversion with a shared pointer. Now this pointer to to an automatic object will be passed around after the function exits, and I will likely get a crash. Ideally, now I'm fantasizing a bit because there is no such thing. I would like the defaults to be inverted, and I want to be able to explicitly say that I want a converting constructor, or at least I would like to have an attribute that says that I want a converting constructor. But for some reason, no compiler ever implemented this, which appears to be an obvious help. Perhaps in the future we'll get one like this. And now to show you that the standard has taken a different route here. And you have something like, we will have in C++ 17 this file system path, which is something different than a string, a dedicated type. But because it has a conversion, it doesn't give me the safety feature that I would otherwise want. I have some functions store contents, and I am applying a good advice that I shouldn't be having two arguments with the same types, put one along another. So this is different types, it's good. But if I pass the arguments the other way around, because I have these implicit conversions, even the compiler sees mismatch, it is forced to apply the conversion and be silent about the bug I am about to implement. This is a different balance between safety and expressiveness, which standard libraries apparently choose. Now for the last part, we have little time, so I have to be fast. There is 100 of ways to initialize a vector, like with these values, with the initial size, with an allocator, and a size with a range, hundreds of ways, and it causes dozens of problems. This is a well-known gotcha with a standard vector, and I will not even go into details with it. But the point is that I can have the same types and values, but only by changing parentheses to braces, I change how the vector is initialized. Now it does something else, perhaps not what I expected, and I will likely get an error sooner or later. Some people say it's a problem with list initialization or initializer list constructors, but I can reproduce the same problem in C++ 98 by only using explicit constructors. If I have two similar constructors, only by choosing direct over copy initialization, a different constructor gets selected. But I don't complain about explicit constructors or copy initialization. I can only complain about my choice of constructors here. And the same goes for vector. The problem is that to say construct a vector of int using two ints is ambiguous, until you tell me whether you want braces or parentheses. And if I have a function in place, if I want to place a vector into a set of vectors, I only pass 4 and 2. It doesn't know, or it has a problem, which one to choose, and it may choose a different one than you think. By the way, how do you think which one gets selected here? You see, that's the problem with the vector. Another problem. This is how I initialize a vector with the initial capacity, or size, or capacity. Do you know if this 64 is initial size or capacity? Size, it's size. The second time you always get it right. And the first time, if you come from Java, in Java, this 64 would mean initial capacity. You will for sure get it wrong. And do you know why the vector doesn't have the constructor with initial capacity? The answer is quite obvious, because it would require you to type to give a size t argument, but this is already taken by the constructor taking initial size. So, sorry, you can have both. And there are more problems. Like this, we have two vectors, but now we don't know the type. One is parameterized by I, the other is parameterized by j. I want vi, the second vector, to have the same elements like vj, but converted to I, whatever this is. So I use the range constructor. And this is my intention is reflected by this assertion. Is this assertion correct? Now this is a question to you. So we've been programming for a long time in C++, but nobody wants to give a definite answer. The answer is, it depends on what I and j happen to be. If I instantiate the template so that the second vector stores iterators to the first vector, this is only an element that is good to be pushed back into the vector, and this actually creates a vector of two iterators. The point being, and even before we go to the next slide, that it is not you who control which initialization scheme gets chosen. Only the types control it, and you may not know the types, or you may not know the conversions that are involved. The same problem is if I have a vector of any, like boost any, or in C++ 17 we have in the standard library a similar thing. You know what it is. It's like a void pointer, but with value semantics. This is what it is. It can store any type. It has a conversion from any type whatsoever in the word any, and you can store anything inside and copy it around. So I have a vector of 5 integers, and I want 5 integers both type erased. I use this constructor, and unfortunately I get something else because the way the initializer list constructor works, this any would rather hold a type erased iterator. So what I get is 2 type erased iterators instead. So yes, this basically sums all those issues with using a vector. We wouldn't have this problem if we used, I don't recommend this, but if we just default initialized the vectors and then use init function to properly initialize the values, we would at least have a chance to have a name, and in this name we would reflect what we want. But this is a problem with the constructors, that they don't have names. Some people, perhaps in another language, in another reality, we would have a language feature that allows us to give names to constructors, or at least to constructor parameters. But for now, this is not within range. Some people deal with it by providing factory functions, and it works to some extent, but you are returning something from a function. So we know there is a copy elision, and in C++ 17 there will be a mandatory copy elision in some cases, but not all. And if we want to emplace a vector in a set of vectors, if we use this factory, there is no way we will trigger a move constructor. And it takes time, even a move constructor. And if you applied it to other types may not be movable. So it may not be a solution. A good solution for this problem is to use a tag, is to use an artificial type only to select a different constructor, only for it to be able to have a name. A tag is an empty class with single value, and you can use it to add additional overloads. Like I have 2 overloads with the same set of meaningful parameters, but now they differ by this tag. And I choose the right overload by giving you the right tag. It makes little sense for normal functions, but it is an ideal solution for a vector. If I wrote my own alternative vector, I will not do it. I would give it different constructors. Probably all the constructors would have tags. And then the tag alone, well, one with values, we can leave it without the tag, but all the others have a tags, and this tag clearly reflects what I want to do, how I want this to be initialized. It's not the types that dictate how I want to initialize it, but me by providing this or the other tag. And even if I want to place this vector in a set of vectors, I can pass a tag along, because from the type system's perspective, it's just another type. And it knows how to forward it and create my vector the way I want in place. Probably provided, but now the emplace would have to use brace initialization in a STL2. This is perhaps what we could have. And the same examples from the previous slides, they are all fixed. Like 5, 6 If I want this to mean a size, I can use just different tag. Giving a pointer may represent two iterators, may represent a range, but I will say it explicitly. It's either range or a compile time error. It may be a normal value stored in a vector in other cases, but I say it explicitly. Either value or an error. And all those problems are solved, except for the problem with any. This is not solved by even tags, because any has so powerful a conversion. This omni conversion really kills every safety feature, so I can only recommend don't use brace initialization where you suspect your type has an initializer list. If you have to, don't use any in vectors. If you insist on using this, don't complain that you have bugs. And it solves other problems also, like if I have point and I may need to initialize it with polar or Cartesian coordinates. In both cases, I need to pass two doubles. I can disambiguate by using different tags. And this is to show you that I'm not inventing this. The standard library in other places already has applied it. And this is a spectacular example. There is 5 ways to initialize a log over a mutex, and they are disambiguated by using different tags. And that's it. I think we fit into our time. If there is any message I wanted to send with this talk, is that you can think of the code as not only a ways of implementing fast binaries, but also as a means of communication to other programmers and to other tools that can help you if you help them. For some particular advice, really make use of compiler warnings. They can really save your day. And you can use, this is what we do at our work, more than one compiler. Like we compile our binaries, we generate the binaries with the GCC, but we are also doing a Clang pass, only for it to detect, to give us warnings and detect bugs that the other compiler failed to. Use more constraint types, those that only do the thing you want and nothing else. And try out the explicit library, which already implements those types that I was showing you. It's on my GitHub page, so if you just Google explicit library, it will probably show up. Thank you.